there are four major currents responsible for the electrical activity of the heart. Or we can say, to understand the behavior of cardiac potential and the electrocardiography, we have to focus on these four currents. These four currents are the sodium current, potassium current, calcium current, and last one is the funny current. Though we have to understand about the mechanisms of these current, but there is another current, we can call it chloride current. At any time when cell is at a resting position, the sum of all the currents is actually zero. It means there may be individual current may be present. Suppose sodium current may be present, some net sodium current may be present. But if we add all the currents, the sum of all the currents is zero. When cell is at resting membrane potential, means the potential of the membrane is not changing. Whenever resting membrane potential or membrane potential goes positive or depolarized, means some net positive current enters the cell. When resting membrane potential depolarize, means if it is minus 90 millivolt, it goes to, let's say, minus 60 millivolt. It means it depolarized. Means some net current enters the cell. Another case, if it hyperpolarize, means the potential goes more negative, let's say minus 100 millivolt. It means some net current goes outside the cell. Now, these currents, these currents are basically the ionic currents. These are not the electronic currents. As we have learned in our high school, electronic currents are due to battery. Battery has a positive terminal and a negative terminal. Positive terminal means here there the voltage is at high value, and negative terminal means voltage is at lower value. So current flows from a high potential to a low potential. But in case of ionic currents, we have to learn about their forces. What are the forces that is responsible for these currents? There are two forces that are responsible for the ionic currents. One force we can call it the chemical gradient. One force we can call it the chemical gradient. Chemical gradient means, just take an example of sodium. Let's say sodium ion outside is in high concentration and sodium ion inside is in lower concentration. So chemical gradient, direction of chemical gradient is outside to inside, means from high concentration to low concentration. But another force is the electrical gradient. Another force is electrical gradient. Means this membrane is actually positive outside and negative inside. If you put a sodium ion here, where it will want to go? It will want to go inside because it is a positive ion. It will go towards the less potential or low potential. So electric gradient is also inside. We can apply the same thing or same thinking to the potassium ion also. In case of potassium ion, as we know, chemical gradient, you will write delta C. Potassium ion outside is in less concentration and inside is in higher concentration. So chemical gradient of potassium ion is in this direction. However, cell is positively charged outside and negatively charged inside. So potassium ion wants to come inside. So electrical gradient is inside the cell. So there are two forces acting on the ions. Now, how to calculate the net force? So there is a formula we can apply. From this formula, we can find out the net force acting on any ion. This is known as the electrochemical gradient, and it involves, this is the resting membrane potential or the membrane potential minus the nurse potential of that ion. As we know, Nernst potential of any ion is calculated by this formula. Let's say for potassium it is inside minus potassium concentration outside. So what I want to tell here means Nernst potentials involves the inside and outside concentrations, and these concentrations are maintained by the sodium potassium pump. So this is the ultimate battery. Okay, so from this formula we can find out the net electrochemical gradient or net force acting on the ions. So we have some examples here. Let's say for sodium, outside concentration is 145, inside is 15, and based on these, its Nernst potential comes out to be plus 61 millivolt. And the, let's say, potential of the membrane is minus 60. So what is the net force? Minus 60 minus 61. So it is minus 121. So when it comes negative, it means force is acting inside. Negative means force is acting inside. In case of potassium ion, outside concentration is 4.5 millimoles. Inside concentration is 120 millimolar, and from this we can find out the Nernst potential that comes out to minus 88 and millivolt, and the membrane potential is still minus 60 millivolt. So Vm minus 60 minus minus 88, that comes out to be plus 28. So net force acting on the potassium ion is plus 28 millivolts. So this is the electrochemical gradient on potassium ions, but it is positive. It means it will drag the potassium ion outside. Similarly, we can find out the net force on the calcium ions. Calcium ion concentration outside is 1.2 millimolar and inside concentration is about 10,000 times less, that is 0.0001 millimolar. And from this we can find out the Nernst potential. It comes out to be 125 millivolts, and Vm minus 60 minus 125 comes out to be minus 185. So it is a high force acting on the calcium ions. So it is again a inside force. It will drag the calcium ion inside. So these are the forces on these ions. So I hope you understand what are the forces acting on these ions. And if you can remember, sodium ion, the net force usually is inside, and potassium ion is outside, and calcium ion is inside. But these all forces is depend on the concentration inside and outside, as well as on the membrane potential. Now, another thing after force is the conductance. As we know, plasma membrane is a lipid structure, and when ions cross this membrane, they need some sort of channels because they can't cross the lipid bilayer. So we need some channels. So we have to learn about channels, and channels over the cell membrane, number of channels and their state decides the conductance of the uh, conductance of the ions. So every ion, we can say current is basically this is the force and this is the resistance. So we can inverse the resistance and we can call it a conductance or permeability. We can call it conductance or permeability. Now somebody may ask from where the resting membrane potential comes out. How we will calculate the resting membrane potential? Here also we can use the same principles of net current and we can find out this equation. So we are not going in the details, but we can take out the message from here. Resting membrane potential depends on the permeability and the Nernst potential, and Nernst potential depends on the ionic concentrations of those ions, and ionic concentrations are maintained by the pumps. Okay, sodium potassium pump in case of sodium and potassium. So from this formula we can see the ion whose permeability is higher determines the resting membrane potential towards its Nernst potential. Suppose if permeability of potassium is usually higher, or it is about 100 times higher in most of the cells, so the resting membrane potential is nearer to the nurse potential of the potassium ion. We will see one more application of this thing, and the application is this. Let's see, this is a normal cardiac action potential. So what happens when there is ischemia? When ischemia occurs, oxygen delivery hampers, and because of that ATP production also decreases, and when ATP production decreases, the pump capacity of the sodium potassium pump decreases. So once pump capacity decreases, the ion concentration, it is difficult to maintain the ion concentration across the cell membrane. When ion concentration disturbs, then nurse potential also changes, and with this leads to the change in the resting membrane potential. So we can say whenever there is ischemia, the resting membrane potential goes upside, or it depolarizes. It depolarizes. Now we can use this concept to understand the difference in the potentials of the slow and fast cardiac potentials. As we know, fast cardiac potentials, resting potential is about minus 90 millivolt. However, the maximum diastolic potential in slow cardiac potential is 60 millivolt. The reason is SL nodal cells and AB nodal cells have low potassium permeability, and these have high potassium permeability. So because of the high potassium permeability, the resting membrane potential is near to the nurse potential of the potassium ion, that is about minus 88 millivolts, and here the potential is at minus 60 millivolt because of less permeability of the potassium ions. So after talking about the force acting on the ions, we will talk about the conductance part. As far as conductance is concerned, ions need some sort of transport proteins known as channels. Channels are characterized by gates. Channels are some sort of proteins having the gates. Gates can be either in open state or in closed state. If they are in open state, ion can pass the membrane. When they are in closed state, ion can't pass. So there are two states, closed and open. Now the opening and closing of gates is decided by two mechanisms. One is the voltage dependent mechanism and another is the time dependent mechanism. First we will talk about the voltage dependent mechanism. Let's say there is a cell. On that cell there are 10 potassium channels are, or any ion channels are there. Okay. These channels are in various stages. Red one is say closed and green one is in open state. So you can see among 10 channels, green one is 3. So how many are open? The fraction of open channels are 3 upon 10. What this graph shows as the potential of the membrane is increasing, the opening fraction increases. So here at some minus 50 millivolt, let's say the opening fraction is something 0.3, 0.4, but as the potential is increasing, the opening fraction is also increasing, and after about some value, all the channels will become open. So this is the voltage dependence of these gates. So such type of gates who opens with increase in the voltage are known as activation gates. Are known as activation gates. Such type of gates are present in potassium channels. Such type of gates are present in potassium channels. Now talking about another type of channels. Some channels have two types of gates. Suppose one gate is activation gate, another is the inactivation gate. So as we already learned about the activation gate. Activation gates opens when the membrane potential is increasing. So this blue graph tells us about the activation gates. Now there are another type of gates which starts closing when the membrane potential increases. So such type of gates are known as inactivation gates. So this red graph tells us about the inactivation gates, and this is the activation gate. both type of gates are present in the sodium channels. So we can see if sodium ion has to enter the cell, both the gates should open. Otherwise, if any one of the gate is closed, it can't pass the cell membrane. So you can see here, if at some potential, let's say minus 40 or minus 30, these all the gates are open. Inactivation gates are open, but all the activation gates are closed. So it is not possible to cross the cell membrane. So once the potential goes towards the positive side, some activation gates starts to open and inactivation gates starts to close. So there is, we can find out the probability by multiplying these fractions. So we can say the overall conductance or permeability is something like this. It increases and gradually it again goes down. So permeability of the sodium channels follows this type of kinetics, and this is responsible for the action potential of the neurons and cardiac muscle cells. So after learning about the voltage dependence of gating mechanism, we will learn about the time dependence. To understand this thing, let's say there is a cell in which there are some channels or having one type of gate, let's say activation gate. Let's say its potential presently is at minus 50 millivolt. And at minus 50 millivolt, only 3 channels are open. Let's say fraction of open channels is 3 upon 10. Now, by some mechanism, if I change the potential of this cell to, let's say, 10 millivolt, and at 10 millivolt I can see here at suppose 10 millivolt, the number of channels that should be opened should be zero point 0.8, means at 10 millivolt the fraction of opening channels should be 8 upon 10. But do you think I can change the potential very fast, at a very instant? But it takes time for the channels to open. So this time, how much time the channels or gates are taking to come to a steady state of this fraction 0 0.8 is called the time constant. So this time constant, if it is of a less value, then gates take less time. If time value of time constant is high, it means these are slow gates, or we can call them slow channels. So we will encounter such terms like slow calcium channels, fast potassium channels. So these fast and slow word are basically the time constants. Okay, could you tell me which of the gates are the fastest? This figure shows the activation gates of potassium channel, this shows the activation gates of sodium channel, and this shows the inactivation gates of sodium channel. So we can see the time constant here is very less, so these are the fastest.